Speaker is Florian Rommel, the PhD student at Hannover University. Yeah, then give it a shot, please.
Do I have to press something?
No, I don't think so.
Oh, it worked. Oh, okay, yeah. Now I know what. Okay, I could have put this. Like this. Okay. That looks good. Okay. So, thanks for the introduction. I'm pleased to present our paper, Threat Level Attack Surface Reduction. What do I mean by attack surface here? Well, we talk about the attacks, or exploit surface to be more correct, that can be used by an attacker to induce malicious behavior in our program. Assume, for example, a server application where we have an initial attack vector, like a buffer overflow, for example, that enables an attacker to modify memory contents. In modern systems, of course, the attacker cannot inject code directly, as executable code is usually write protected, so the attacker must use the existing code to achieve their malicious task. This can be achieved with return-oriented programming, for example, where the attacker creates a chain of return addresses on the stack to jump between small code pieces that we call gadgets, each finishing with a return instruction, jumping to the next one. Basically, the attacker recombines parts of the available code to execute their desired malicious action. So all the available executable code is the attack surface in this case. Well, now, what can we do about this? One possibility is to simply reduce the available code. We call such techniques binary debloating. The goal is to remove code from the dynamic libraries that is not needed by a specific application. This is usually done on the granularity of individual functions. These approaches originate from the desire to have smaller binaries, especially in embedded systems, but also have been proposed to reduce the code available for attacks. On the right, we see an example, and this is a state-of-the-art static debloating approach, and we see that only a fraction of the libc code is actually needed by an VSFTP server, so the white parts can be removed. However, there's still a lot of code present, as you can see, and especially the whole main executable is still completely loaded. So how can we improve this? Dynamic debloating approaches go one step further. In these approaches, the libraries get debloated during the runtime. On the right, we see such an approach, blanket, that's the name. It eliminates all library code, so it basically overwrites it with invalid instructions, and only includes small trampolines for the entry functions of the libraries. So when we call such a function, all callees recursively get restored from a safe non-executable place based on a simple prediction model or on a prediction model. And after returning from the main library function, everything is eliminated again. And this, of course, results in significant code reduction, but sadly, still only for the libraries and not for the main executable, for example. So we have still an overall, poor overall attack surface reduction. So how can we improve this situation? To better understand this, let's have a look at the MariaDB SQL database server, typical server application, I would say. And the first finding is that the main executable actually makes up a significant portion of the process, of all the code. So 60% of the functions, that's a huge portion. So wiping only the libraries will not touch the majority of the code that is present. MariaDB has a classical thread setup with one thread per client connection. And if we look at a single client that only reads from the database, we see that the corresponding thread serving this client only uses 8% of the code, and only 11% of the main binary's code is actually needed. So, the numbers are similar for different workloads, like an insert client or client that only writes to tables. And now if we compare different workloads, so for example, a read-only client and an insert, the corresponding threads share only 44%, in this case, of the used code. So they mostly use different code. So we can conclude, to more effectively reduce the available code, we must consider the main binary, and we should also consider different thread contexts, because they don't share a lot of code, as it seems. And that's where thread-level attack surface reduction comes in. It's a dynamic approach, like Blanket, for example. It operates during the runtime and restores functions on demand. This is not entirely new, but unlike other approaches, it also considers the whole process, not only the libraries, but also the main binary. And it can work on per thread level, meaning it can debloat different threads individually from each other. First let me illustrate the basic idea of the approach. For example, we can use TLASR to eliminate all the code in our process, except for the entry point, like the main function or the thread start function. And as soon as we call another function, it gets restored. And it remains loaded afterwards until we manually wipe it again. And this applies to functions in the main binary as well as in the libraries. And this is specific to the individual thread. So other threads are separated in terms of code and may have a different set of loaded functions, as we see here. But these threads are still in the same process, so they operate with the same data and work as normal threads. Well, how does that work? Before I describe the thread separation technique that we use, let me introduce first our elimination and restoration mechanism. The elimination framework we created is called CTE, that stands for context-based text elimination, and it's comprised of two parts. First, a static binary analysis tool, it's called CTE meta, that gathers call graph information from the binaries, so executables and libraries. And this works ahead of time. It only needs normal F binaries with symbols, so no source code or debug information is required. And the core of the approach is libcte, a small runtime library, and this library does the heavy work of eliminating functions and loading them again at runtime, as I just described. It uses the CTE meta information to validate the function restores which happen on calls. Currently, it needs manual integration into the program. So how does elimination look like? libcte has two modes of elimination. The first is called killing. If we kill a function, we remove it for this thread without the possibility to lazily reload it. So killing means the entire function is replaced by trap instructions. If an attacker now tries to use some code inside this function, the trap triggers and the program crashes. The second mode is called wiping. and wiping allows dynamic restoration of the function. Not the entire function is replaced with debug traps, but at the beginning we install a small implant that calls the restore handler when we call the function from its correct entry point from the start. The handler first does some validations. It checks if we come from a valid call site based on the return address on the stack, and then it does a call graph validation based on the statically gathered CTE meta information. When the checks were successful, then it restores the function bodies from a non-executable safe place. Now we come to the separation of threads. For this, we use a kernel extension that we originally developed for the purpose of live patching of applications. It's called address space views, and it was first presented at OCI 2020. This mechanism allows multiple synchronized address spaces in a single Linux process. So normally each process has only one address space, as we can see here. All the threads operate in this address space. But with address space views, we can make a clone of this address space. We call this a view, so we have two views here now. And a view is similar to a forked address space, but with all the memory regions shared, except for regions marked as explicitly unshared, like we do here for the text segment. And these regions will use a copy on write mapping between the views. So we can modify the text section in one view without influencing the text section in the other views. Of course, the creation and deletion of memory regions in the address space is also synchronized between all the views. Threads, of course, can switch between views. In our case, we want to have one view per thread. So how does that actually look like if we use TLASR in our MariaDB example? The initialization is simple. We first initialize the CTE data structures to save the function bodies to the safe non-executable place and read the static call graph information that was generated ahead of time. And the second function unshares the text segments from the main executable and the libraries. And it just marks them so we don't create views yet. In MariaDB, each worker is started with this MySQL thread create method. This basically ends up creating a new thread and executing do handle one connection in this thread. And this function in return executes the actual commands from the client in a loop until the connection ends. Now we can use CTE. We first create a new view, then migrate the thread to this new view, and next we wipe everything. This is achieved by first creating a wiping rule set. In our case, it simply says wipe all the functions, and then we trigger the elimination by calling CTE wipe. If we want, we could have fine granular control over which functions to wipe, kill, or which functions remain loaded, but we don't use this in this scenario. So after CTE wipe everything, but the entry function which we are currently executing is wiped and gets restored on demand. So how does it perform? For MariaDB, we see that we can eliminate a significant amount of code, depending on the benchmark from 95 to 97% of all functions, of course also including the main executable and the libraries. But also for smaller applications like Memcached, and in-memory database or in-memory cache, we see similar numbers. Here we have a different thread model, so no per connection threads, but a thread pool, so a fixed number of worker threads. And so we wipe once per thread instead of once per connection for Memcached. But yeah, the numbers are similar. But do we actually prevent attacks? To investigate that, we try to conduct automated ROP attacks. And as you can see, the auto-ROP utility is able to conduct an attack in the original MariaDB and Memcached servers, and also in statically debloated variants, but not in our TLASR-enabled servers. We also did a bunch of other really interesting benchmarks, also with other applications, but yeah, sadly, I have no time for them. So have a look at the paper for more information. Finally, let's have a brief look at the performance. We measured the request latencies that clients experience for an increasing number of clients, up to 32, as you can see. And for Memcached, the average latencies of the TLASR-enabled variant closely matches the latencies of the baseline unmodified program in most cases. For MariaDB, where each client connection has its own thread in the server, we see that the TLASR overhead over the baseline is small for few threads, but increases as the client count rises. And yeah, this is primarily due to the address space view mechanism, which causes additional context switching costs on every thread switch. Basically, we have to switch the address space also. Yeah, so the overhead starts to become noticeable when the number of working threads surpasses the number of CPUs. In our case, we had 4 CPUs here. Yeah, for MariaDB, we also experimented with rewiping. That means wipe again after a transaction or a bunch of transactions. And as you can see, if we do not make it too often, like after every single transaction, it's not much more expensive than only wiping once per connection. Yeah, that was TLASR, a new approach to reduce the attack surface of programs. Thank you for your attention, and now I'm happy to answer your questions.
Right, Q&A time. Excuse me. Any question? Yes, please.
So when you say that your approach prevents the ROP attacks, right? So is it just like random, the ROP attack thing, does it just randomly test the application, or is like guaranteed that there is no ROP attacks in your?
Of course, it's not guaranteed. So what the auto-ROP utility does is you give them basically an image of your loaded binary, and then it finds all the possible ROP gadgets. So it has a database or of possible gadgets. They must have a return at the end, and there are different types for chumps and all kinds of computations. And then it tries to conduct an address and land in some C library function to do arbitrary computations. So that's what that thing does. Of course, that's no guarantee that we couldn't manually find some attacks. So, but at least it's a good sign that you cannot, at least with this tool, automatically do it. So, yeah.
Thank you.
Any more question? Yes.
Just curious, does your mitigation target any other types of vulnerabilities apart from ROP? Is that something you evaluated?
Yeah, that's a good question. So do we target any other vulnerabilities? Yeah, basically all code reuse vulnerabilities. So there are like variants of return address programming where you can, for example, exploit chumps in a similar way. So these are, of course, also targeted. Yeah, so I don't know of attacks that are totally different. So they all work like in a similar way. Okay, we can use indirect chumps and stuff. So, but yeah, basically these kinds of attacks.
Okay. Any other question? I do have a question. We need to do like kill, wipe, restore with this scheme, but I thought like the performance overhead must be huge, but it seems like it was not. So can you let us know the secret sauce of this?
Yeah, yeah, the performance overhead. Yeah, as we can see, the performance overhead of the CTE is quite low. So most of this arises from the thread separation, and the question is why? Because we do it only once, and then the function remains loaded. So until we manually rewipe. So like we can see here, in this graphic on the right, we see that if we rewipe everything after each transaction, then the overhead is really high. That's the second bar, the high bars. It's even a logarithmic scale. So but if we do the net not too often, then yeah, we just the overhead diminishes because the loaded functions stay loaded, and yeah, and then we very fast have a set of loaded functions that are actually used, and yeah, then we don't have any overhead anymore. Yeah.
Thank you. Any other question? Let's do thanks to our speaker again.
Thank you.